Hello, Alife. This is George Jenkinson. I'm going to be presenting our paper Spider, a Bioinspired swarm algorithm for adaptive risk taking. So Spider stands for Swarm Personality for Density Response Algorithm, and it's based on the idea of boldness in biology. So an example of boldness in biology is Stegodyphus dumicola, a social spider who have a spectrum from shy to bold that allows them to take on tasks that have different risk appetites for hazards. So a shy spider will take part in maternal care and maintaining nests, whereas a bold spider will go out hunting and have more of an appetite to take risks. Now, the social spider Stegodyphus dumicola maintain a boldness distribution over the swarm that's appropriate to the size of the swarm that they have, and it does this in a completely decentralized way, which I'll run through now. So you may have two spiders that come into contact with each other. One is shy and one may be bold. In such a case, it's likely that the shy spider will increase its boldness by a small amount, and that's mechanism number one. So mechanism number two is that if a spider has just increased its boldness by an amount, it's more likely to do so again if it's in contact with a bold spider. And the third mechanism is that if a spider then becomes alone at any point, its boldness will slowly decrease. So these variables, how much spider's boldness increases by and how much the spider's boldness decreases by, control the risk appetite of the wider swarm, and they make it appropriate to various tasks. So it would be useful to be able to harness this risk appetite, this mechanism for risk appetite, to control swarms to take appropriate risks in, for example, exploring a hazardous environment such as Fukushima, or an unknown environment such as a planetary surface or underwater. So we wanted to make a task where we could test this, we could demonstrate this. So we use simple robots, kilobots, which are very small, coin-sized robots with a very small communication region. And we associated their boldness with the risk appetite of exploring an arena where the risk was becoming disconnected. So as they get to the periphery of the arena, they're more likely to be isolated and become disconnected from the swarm. And if they're shy, they'll go to the center where they're much more likely to be connected with other robots. So we came up with a way to score how good swarms were at this. And the way that the scoring works is that bold spiders, such as this one on the top left, are disconnected, so it won't score at all, whereas spiders such as any on this yellow-orange line and any on this blue line are connected to the central hub, so they will be scoring the number that is associated with the maximum distance that they're connected to. So in this case, it's a distance of 5 and 4, as represented over here. So as I alluded to earlier, there are variables that control the risk appetite of the swarm, of the wider swarm, and that is namely how much a spider's boldness, robot's boldness ought to increase by when it comes into contact with another, and how much it decreases by when it's isolated. So we came up with an evolutionary algorithm to optimize these two parameters, and this is an early example that's far too shy. So it's safe to say that in this example, the spider's boldness isn't increasing enough to get any kind of useful boldness. So you see quite quickly all of the robots become shy, and they all cluster around the middle, and the score, which is taken every half second from the slide I showed previously, is around 53,000. Another opposing mechanism, or another opposing set of variables, lead to the swarm being far too bold. See, every now and then these kilobots are coming back to the center and scoring small points, but most of the time they spend completely disconnected around the edges. So that's represented here on the right. As time goes on, it quickly becomes a very bold and not very useful swarm with a low score of 18,000. And somewhere in the Goldilocks zone in the middle, we get a swarm who distribute themselves into an appropriate number of shy spiders, which are blue, medium spiders, which are grey, and every now and then bold spiders, which are represented by these red spots. And you can see on the right, they've got something like an even distribution between them, although even isn't necessarily the best for the task. They score much higher, with nearly 72,000. So we optimized a stable swarm for a task, and to show that it's adaptive, we artificially altered the kilobots so that they had a very shy distribution at around 1500 seconds, which will happen in just a second in the video. And then at 3000 seconds, we artificially altered them to be incredibly bold. And after both situations, they settled back down to a reasonable distribution. And another task that we did was we simulated the destruction of large portions of the population, which might be due to falling nuclear debris, or due to the robot breaking down itself. And here we see at 1500 seconds and 3000 seconds, we halved the population, but didn't change the control algorithm. And you can see that the proportions are able to reach a new distribution of shy, medium, and bold spiders. So we'd like to try this on new geometries in two dimensions where you have perhaps two different boldnesses in X and Y. Something to move away from an evolutionary algorithm where the boldness rates can be adapted as the killer are alive rather than set beforehand, and perhaps on mixing the platform with something like an aerial robot and a terrestrial robot to see whether tasks can be optimized in such a situation. Thank you for listening.